Is the universe infinite? People ask me this all the time, and the answer depends on something we don't fully know yet. How much matter is out there? How strong gravity really is? But let me tell you what we do know and what the mathematics predicts, because the possibilities are far stranger than you might expect. Space itself is expanding right now. Galaxies billions of light years away are racing away from us at thousands of miles per second. The farther they are, the faster they're moving. The space between them stretching, growing. Every second, the universe gets bigger. You can't feel it. The effect is too small here, but it's real. And here's what that means. If space is expanding now, then in the past, everything was closer together. Run time backward, galaxies get closer, denser, hotter. Keep going, further back, further, until when? Until everything, every galaxy, every star, every atom was in the same place, compressed into something unimaginably small and dense. That moment, that beginning, we call it the Big Bang. Not an explosion in space, the explosion of space itself, the moment when everything began. But let me tell you how we figured this out and what it means, because the implications are far stranger than you might think. In the 1920s, astronomers started looking at distant galaxies, measuring their light, and they noticed something peculiar. The light wasn't quite the right color. It was shifted toward red. Red shifted. Now you might think, so what? Light changes color all the time. But this was different. The shift followed a pattern. The farther away the galaxy, the more its light was red shifted. Not a little, a lot. What causes this? Motion. When something moves away from you, its light gets stretched, like sound from a passing car. As it moves away, the pitch drops. Same thing with light. Motion stretches the wavelength, makes it redder. Okay, space is expanding, has been since the beginning. But here's the question that kept me thinking. What happens next? Does it expand forever, or does something else happen? The answer depends on one thing: gravity. Everything in the universe has mass. Mass creates gravity. Gravity pulls. Even though space is expanding, even though galaxies are flying apart, gravity is working against it, trying to pull everything back together. It's like throwing a ball upward. The ball rises, but gravity pulls it back. Whether it comes back down depends on how fast you threw it. Throw it slowly, gravity wins. The ball rises, slows, stops, falls back. Throw it faster, at a critical speed, escape velocity, the ball just barely escapes. It keeps rising forever, but its speed approaches zero. Throw it even faster, it escapes easily, keeps rising, never comes back. The universe is the same. Everything depends on the balance. How fast is space expanding versus how hard is gravity pulling back? And that gives us three possibilities, three ways the story could end. The first possibility is this: space expands too fast. Gravity can't slow it enough. The universe expands forever. Galaxies race apart. Eventually they're so far that light from one galaxy can never reach another. Each becomes isolated, alone in an ocean of darkness. Stars burn out one by one. Everything goes cold, dark, empty. The universe doesn't end in drama. It just fades, gets colder and colder, and more empty, until nothing interesting can ever happen again, forever. The second possibility is this: space expands at exactly the critical speed. Gravity pulls back just hard enough to slow the expansion, but not stop it. The universe keeps expanding forever, but slower and slower. At infinite time, the expansion rate approaches zero, perfectly balanced on a knife edge. This is the flat universe, and its fate is similar to the first case. Expansion forever, but balanced precisely at the critical rate. The 30 possibility is this: space doesn't expand fast enough. Gravity is too strong. The expansion slows, then stops, then reverses. Galaxies stop receding, then start approaching. Space begins contracting. Everything gets closer together, denser, hotter. Think of the Big Bang in reverse. Galaxies collide, merge, stars are ripped apart, matter gets compressed, temperature rises. Eventually space contracts so much that atoms can't exist. Then molecules, then ends in fire. Everything that exists gets crushed back into what? A singularity again. Maybe another Big Bang. Maybe something else. We don't know. Which one is our universe? In the mid-1960s, we didn't know. The answer directly. And while I was thinking about this, about the universe expanding or contracting, I realized something. If the whole universe can collapse, what about smaller objects? What about individual stars? Stars are remarkably stable for millions of years, billions even. They burn hydrogen. Fusion reactions in the core release energy. Radiation pressure pushes outward. This balances gravity trying to crush the star inward. But nothing lasts forever. Eventually, the fuel runs out. Hydrogen is exhausted. Fusion slows, then stops. The outward pressure disappears, and gravity wins. For small stars, stars like our sun, this is relatively gentle. The star cools, contracts, becomes a white dwarf, an Earth-sized ember made of compressed matter, hot at first, but cooling over trillions of years, eventually becoming a cold, dark sphere, a stellar corpse. But for massive stars, something different happens, something violent. When fusion stops in a massive star, the collapse is catastrophic. The core implodes in seconds. Electrons are squeezed into protons. They combine, forming neutrons. The core becomes a neutron star, a ball of pure nuclear matter, the size of a city, but with the mass of the sun. The density is beyond comprehension. A teaspoon of neutron star matter weighs as much as a mountain. Gravity at the surface is so strong that if you dropped something from 1 meter up, it would hit the surface at a significant fraction of the speed of light. But neutron stars have a limit, about 1.5 solar masses, the Chandrasekhar limit. They can only support that much. Push beyond that limit, and even neutron pressure can't hold the star up. Then what? The collapse continues. And this is where things get really strange. I started looking carefully at the mathematics. The equations describing gravity near a massive, dense object. These are Einstein's equations, general relativity. For normal objects, planets, stars, even neutron stars, the equations work fine. They predict how gravity behaves, how time flows, how space curves. But when you squeeze matter beyond a certain density, something odd appears in the math, a critical size, a boundary. For any given mass, there's a size below which the equations predict something bizarre, a point where the mathematics says time stops, where space curves back on itself completely. We call this the Schwarzschild radius, named after Carl Schwarzschild, who found this solution to Einstein's equations back in 1916. For the Sun, this critical size is about 3 kilometers across. For Earth, it's about 9 millimeters, the size of a marble. For any object, you can calculate this critical radius. It depends only on the mass. The more massive the object, the larger the critical radius. But the critical radius grows slower than the actual radius of the object. So normal objects, stars, planets, are nowhere near this limit. Their actual size is much, much larger than their critical radius. But if you could somehow squeeze the sun down to 3 kilometers across, or Earth down to a marble, you'd hit this boundary, this critical circumference where the math stops making sense, where something very strange happens. An object compressed below its Schwarzschild radius, a collapsed star. That's what we called these things in the mid-1960s. Some people also said frozen star, for reasons that will become clear, or black star, because no light escapes from them. Whatever you called it, the predictions were bizarre. And the strangest prediction involved what happens to someone who falls into one. Let me describe a thought experiment. Forget the mathematics for a moment. Just imagine this scenario. A massive star is collapsing. Its core is imploding. Gravity is crushing it smaller and smaller. And imagine someone, an observer, standing on the surface of this collapsing star, riding it down, falling inward with it. Now imagine you're far away, safe, watching through a telescope. What do you see? At first, nothing unusual. The star shrinks, gets smaller, denser. The observer on the surface falls inward. Light from the surface travels to your telescope. You see him there. Maybe he's waving, dancing, sending light signals. But as the star approaches the critical size, the Schwarzschild radius, something strange starts happening. The light reaching you from the surface changes. It gets redder, dimmer. This is gravitational redshift. Light climbing out of a strong gravitational field loses energy. Its wavelength stretches. It shifts toward the red. The stronger the gravity, the more the light is redshifted. And as the star approaches the critical radius, the gravitational redshift becomes extreme. But that's not all. Time itself is affected. The observer's movements appear to slow down. He waves his arm, but normally. But the light carrying that information to you is being stretched by gravity, delayed. As the star gets closer and closer to the critical size, the effects become more extreme. The observer moves slower and slower from your perspective. His light gets redder and redder, dimmer and dimmer. Finally, as the star reaches the Schwarzschild, forever falling but never quite crossing. Time has stopped for him, at least from your point of view. His light is so redshifted, it's essentially invisible. He's frozen at the edge of this collapsed star for all eternity. This is why some people call it a frozen star. From the outside looking in, nothing can ever cross that boundary. Everything just slows down and freezes there. But here's the really mind-bending part. What about the observer's perspective? What does he experience? Nothing. Nothing at all. From his point of view, time passes normally. He doesn't slow down. He doesn't see anything unusual. The critical boundary, the Schwarzschild radius, he passes right through it. No warning, no sign, no jolt or discontinuity, just smooth, continuous motion inward. To him, it takes maybe a few seconds, a minute, some finite time. He crosses the boundary without even noticing. But once he's crossed, something has changed. He tries to send a signal out, a radio transmission, a light beam, anything, and it doesn't work. Not because the signal is blocked, but because space itself is so curved near the collapsed star that every direction is inward. There is no outward anymore. All paths, every possible trajectory lead deeper into the star, toward the center. He's trapped, can't communicate, can't escape, can't signal for help. And from his perspective, he just keeps falling. eventually reaching the center where tidal forces become infinite and everything is crushed. The math breaks down there. We don't know what really happens. From outside, you see him frozen forever at the boundary. From inside, he fell through in finite time and is doomed. Both descriptions are true. They're just two different perspectives on the same physical reality. Because time itself flows differently in different places. Near strong gravity, time runs slower relative to distant observers. And at the Schwarzschild radius, from an outside perspective, time essentially stops. This might sound like science fiction, but it's not. Time really does flow at different rates in different gravitational fields. We've measured it. Your head ages faster than your feet. Right now, not much, but measurably. Your head is slightly farther from Earth's center. Gravity is slightly weaker there, and time runs slightly faster. Over your entire lifetime, your head will age about 90 billionths of a second more than your feet. You can't feel it, but it's real. In 1960, just a few years ago, physicists did a beautiful experiment, the Mossbauer experiment. They took a photon, a single quantum of light, and dropped it 24 meters from the top of a tower to the bottom. And they measured its frequency when it arrived. The frequency had changed, shifted, because the photon fell from a region where time runs slightly faster to a region where time runs slightly slower. The shift was tiny, 1 part in 1,000 trillion, but they measured it, proved it. Time really does flow at different rates. Near a neutron star, the effect is dramatic. Time at the surface runs maybe half as fast as time far away. An hour there is 2 hours for distant observers. And near the Schwarzschild radius of a collapsed star, time, from a distant observer's perspective, essentially stops. An hour for the falling observer might correspond to billions of years, infinity technically, for distant observers. This is why the falling observer appears frozen. He's not frozen from his own perspective, but time is running so differently for him that from your point of view, he might as well be stopped. Earth's core is younger than its surface, about 2 days younger, because time runs slower down there in Earth's stronger gravity. Over 4.5 billion years, that adds up to about 2 days of difference. This isn't speculation. It's not theory in the sense of maybe it's true. It's measured, confirmed by the Mossbauer experiment and others, as real as anything in physics. So, if these collapsed stars exist, how would you find them? They don't emit light, by definition. Light can't escape from below the Schwarzschild radius. They're invisible, dark, holes in space where stars used to be. I thought about this problem, and there are a few possible methods, all indirect, all difficult, but possible. First, binary star systems. Most stars aren't alone. They have companions. 2 stars orbiting their common center of mass. If one of them collapses, becomes one of these black stars, you'd see something odd. A visible star seemingly orbiting empty space, but not really empty. The visible star is being pulled by something massive, something invisible. You could watch the visible star's motion carefully, plot its orbit, calculate how massive its unseen companion must be. If that mass exceeds the Chandrasekhar limit, if it's too massive to be a neutron star, and if the object is dark, then maybe you found one, a collapsed star. This is actually one of the more promising methods. Many stars are in binary systems. If collapsed stars exist, some of them must have visible companions, and we should be able to detect the gravitational effects. Second, gravitational lensing. Light bends near massive objects. Einstein predicted this back in 1915. The sun bends starlight. We measured it during the 1919 eclipse. proved Einstein right. A collapsed star would bend light even more dramatically. If light from a distant star passes near one, the light curves. The collapsed star acts as a gravitational lens. With perfect alignment, collapsed star, distant star behind it, and you observing, you might see the distant star's light bent around the collapsed star, distorted, maybe multiple images, maybe a ring of light. The probability of such perfect alignment is small. You need the collapsed star, the background star, and your telescope all lined up precisely. The odds are terrible, but might give us the right alignment. In the mid-1960s, some of my colleagues had ideas about collapsed stars that I found unsatisfying. One popular theory said that stars simply can't collapse below the Schwarzschild radius. They can't become these frozen stars or black stars. Do something to avoid collapsing completely. It will explode, throw off mass in a supernova, anything to get below the limit. Because if it didn't, it would keep collapsing past the Schwarzschild radius. And nobody wanted to think about where that led. But this bothered me because it doesn't explain why stars explode. It's just saying they explode because they have to avoid collapsing. That's circular reasoning. It's like saying God causes supernovas so we don't have to worry about collapsed stars. That's not physics, that's avoiding the question. Another attitude, I jokingly called it the all right Jack theory, went like this. I can't see inside the Schwarzschild radius. I can't predict what happens there. The math breaks down at the singularity. So why should I worry about it? As long as I'm safe out here, all right, Jack. This really bothered me, because the observer falling in has a real problem, a real future, a real fate. Just because we can't see it from outside doesn't mean it's not real. It doesn't mean we should ignore it. The question of what happens inside is tricky, very tricky. The math is difficult. Our physical intuition fails. But running away from the question isn't the answer. This argument sort of beats around the bush by not answering anything. If physics predicts something strange, something uncomfortable, we don't get to ignore it just because it's inconvenient. We have to think about it, work through it, try to understand it, even if the answers are strange, even if they're unsettling. That's what physics is about. The question is a tricky one, and it does need some thought. Think about what's happening right now. Somewhere in space, a massive star is collapsing, running out of fuel, gravity crushing it smaller and smaller. And if it's massive enough, if it exceeds that critical limit, it won't stop. It'll keep collapsing, past the Schwarzschild radius, past the point where even light can't escape. From far away, someone watching sees it slow down, freeze. The star appears to stop at the boundary, frozen there forever. Time itself has stopped from their perspective. But an observer on that star, they experience nothing unusual. They cross the boundary in seconds, minutes, normal time. Then try to signal out and can't. They're trapped. Space itself has curved so completely that every direction leads inward. Both observers are right. Time really does flow differently for them. This isn't philosophy, it's measurement. The Mossbauer experiment proved it. Drop a photon 24 meters and its frequency changes. Your head ages faster than your feet. Earth's core is younger than its surface. Everybody knows time flows, but you have to stop and think about it to really grasp what that means. Time isn't the same everywhere. It bends, stretches. Near strong gravity, it can slow to almost nothing. And space is expanding right now. Galaxies racing apart. We can measure it, see it in the redshift of distant light. Run time backward and everything collapses to a point, the Big Bang. Run it forward and maybe space expands forever. Or maybe it all collapses back someday. We don't know yet. Individual stars collapse. Maybe the whole universe collapses or expands forever. The mathematics predicts all of this. Strange things, uncomfortable things. But the math doesn't care about comfort. It just describes what is. Some people want to avoid these questions. Say stars can't collapse that far, must explode first. Or say we shouldn't worry about what happens inside because we can't see it. But that's not physics. That's running away. The question is tricky. The math is difficult. Our intuition fails. But the answer, whatever it is real. The observer falling in has a real fate. Time really does stop from one perspective while continuing from another. These aren't contradictions. They're both true. That's the inconceivable nature of it. Space expands. Time bends. Stars collapse into darkness. And we're only beginning to understand what it means. When you really think about it, really stop and consider what the equations are saying, the universe is far stranger than it appears. Not simpler, but more true.